In this final video portion, we're going to be talking about unit tangent vectors, unit normal vectors, and curvature. These are three different measures of vector-valued functions. So let's start with some definitions. Our first definition is the definition of a unit tangent vector. Typically we write, so the unit tangent vector, typically we write it as a capital T for unit tangent vector. It's a function of t, the parameter of our vector-valued function, and it's defined as r prime of t divided by the magnitude of r prime of t. Let's break down what this means for a second. So we saw last time that r prime of t is the derivative of some vector-valued function. Let's say this is the arc drawn out by a vector-valued function. R prime of t at a given point is going to be the tangent vector at that point. So that's what this piece is talking about. The magnitude of r prime of t we've talked about in real-world terms as the speed. In other words, we're taking this tangent vector and then we're scaling it down by the length of that tangent vector, which will scale it back so that it's exactly 1 unit in length, resulting in a shorter or potentially longer vector, but one that's exactly 1 unit in length and exactly tangent to the curve. Hence, unit tangent vector. It's a unit in length and it's tangent to the curve. Our next definition is our unit normal vector, and it's typically written n of t, n standing for normal, which is equal to, in this case, the derivative of the unit tangent vector divided by the magnitude of the derivative of the unit tangent vector. One thing that's interesting to point out, the tangent vector, the unit tangent vector itself, t, is always going to be 1 unit in length. But once we take the derivative, we're no longer guaranteed that that derivative is going to be 1 unit in length. So really, we're computing the derivative of our unit tangent vector, and then again, scaling it down by the magnitude, or the length of that derivative. Pictorially, I can draw this up on the same picture. Our unit normal vector is always going to be exactly normal to our unit tangent vector. So if this is our unit tangent vector, t, that's exactly tangent to our curve, our unit normal vector, n, is going to be exactly perpendicular to that. And in this case, it's pointing up inward into the curve. Let's go back to real-world applications again. So before, our unit tangent vector is the direction of the velocity. We talked last time about how the derivative itself will yield a velocity vector. Scaling it back will just tell us the direction of that velocity. And because we're taking the derivative of the derivative, our unit normal vector is actually measuring the acceleration direction. It's an acceleration vector. Now, because it's normalized, it's not telling you the magnitude of that acceleration, but it is telling you the direction that you're accelerating in. If you recall from previous calculus courses, acceleration is telling you how you're being pulled along the path. So as I travel along this r of t curve, if I were a particle, the normal vector is going to pull me, in this case, exactly perpendicular to the direction of my course. And that perpendicular pulling is indicated by this curve of the curve. One question that we might ask is, why are these two things normal to one another? There's nothing intuitive about the fact that the derivative of the derivative would somehow be orthogonal to the original curve, or to the original vector. So I'm going to do a quick proof to satisfy your curiosity about why these two things would be tangent to one another. So bear with me a little bit. This is a cool trick. I think it ends up being pretty cool. For the sake of clever mathematics, let's consider the dot product of the unit tangent vector with itself. Now we know by definition that the unit tangent, or a dot product, yields the magnitude of the first component times the magnitude of the second vector times the cosine of the angle between them. In this case, the angle between them is just 0 because they're exactly the same vector. The cosine of 0 is 1. And because we've scaled each of these unit tangent vectors to be exactly 1 unit in length, it means that this dot product is just 1 times 1 times 1, which is exactly equal to 1. The next step, and this is maybe a tricky step, I'm going to take the derivative of both sides. We haven't yet talked about taking derivatives of dot products, and so I want to introduce it here. When I take the derivative of both sides, I'm taking the derivative with respect to t. It turns out that dot products, maybe here I can't quite fit d1 dt. Derivatives of dot products work out just like derivatives of multiplication. So you remember from derivative rules that when we have two terms multiplied by one another and I take the derivative, it's the derivative of the first times the second plus the derivative of the second times the first. And the same thing holds for dot products. So in this case, I'm going to have the derivative of the first t prime of t dotted with the second term, or the second factor, plus the derivative of the second factor dotted with the first. And that's all going to be equal to the derivative of 1. And the derivative of a constant is just 0. Now we're left with these crazy dot products. Notice that I have this term is repeated exactly twice. So I have on the left side 2 times the derivative of the unit tangent vector dotted with the unit tangent vector. That's equal to 0. And I can divide both sides by 2. It'll still be equal to 0. And it tells me that the derivative of my unit tangent vector dotted with my unit tangent vector is equal to 0. The only time that our dot products are equal to 0 is when the two vectors are orthogonal to one another. So that means that t prime and t are orthogonal. And that's exactly the conclusion that we wanted to have, because if you recall, our normal vector is given by t prime of t, and then we shrink it down a little bit by dividing by the magnitude of t prime of t. But because the normal vector is just a shrunk down version of t prime, we know that our normal vector and our unit tangent vector are going to be orthogonal or perpendicular to one another. The final thing that I want to talk about today, and hopefully you can still read this board, I want to talk about curvature. So curvature is one other measure that we have for vector-valued functions. And I'm just going to define it. So the curvature of a vector-valued function, typically written kappa, that's sort of a curly k, of s, I'm going to define that as the magnitude of the unit tangent vector of s, the derivative of the unit tangent vector with respect to s, so I'm taking a derivative of my unit tangent vector with respect to s. Notice, though, that this is only the case when, so this is curvature represented when my input value is arc length. So this is a very special way to write the curvature. The curvature when my input for my r of s function is parameterized. I'm going to start writing in green, hopefully it's clear. Is parameterized by arc length. Arc length. You can't really read that very well. So if we happen to have our function already parameterized by arc length, and we talked about that a lot earlier today, then we can just go ahead and compute the unit tangent vector and take its derivative with respect to this special arc length. However, most of the time when we're dealing with functions, we don't have our vector-valued function parameterized by arc length. And it can be a messy thing to try to convert into that parameterization. We saw what that involves, going from just any old t to this special s. The special s having the property that our speed is constant and a constant value of 1. So typically, to compute curvature, if our function our vector valued function r is parameterized by t, we can do a special conversion. And in this case, we see that our curvature k of t is going to be equal to, actually it turns out by chain rule, it's the magnitude of t prime of t divided by the magnitude of r prime of t. And really briefly, the reason why this works, we can see, here's my proof. If I'm considering t prime of t, my derivative here, if I think of this in terms of chain rule, I can write this as the derivative with respect to arc length, but by chain rule I would have to multiply by the derivative of arc length with respect to time. And notice here that ds dt is exactly the derivative of the distance that's been traveled with respect to time, or speed. And we can write speed as r prime of t. So here we see that this term ends up being, so the ds dt, my ds dt term right here ends up being speed, which is written equivalently as the magnitude of r prime of t, because this is also a measure of speed. And solving, I can divide both sides by the magnitude of r prime of t, and I find that the magnitude of dt ds, if I take the magnitude of both sides, is going to be equal to the magnitude of t prime of t divided by the magnitude of r prime of t, which is exactly the formula that we have up here, because the magnitude of dt ds is exactly what my definition of curvature is. Just a few final words. What is curvature? Notice that unlike the unit tangent vector and the unit normal vector, which were both vectors, curvature isn't a vector. It's going to be a number. You'll get out some number. And in your problem set, you'll see that curvature for straight lines is 0, meaning that there's absolutely no curvature, whereas curvature for things that are really curvy, at that point where it's really curvy, it's going to be a high value of curvature. Hopefully you have enjoyed these last videos, and I will talk to you with your problem sets later.